go with it. Let's go for it. Um, Welcome to 2.5. So first things first, the disclaimer. You guys ready for this? College students have difficulty with this section. This is probably the toughest thing to understand in calculus. How about that? So if you get this really well, yeah, you are a-okay. The rest of it is cake. How about that? Well, almost cake. Just because we're putting in like notation, we're putting in a lot of different pieces, and limits are such a fundamental aspect of calculus. We're going to be using limits, but we're going to be using them because we know them already, right? So it's almost like you're laying the foundation, and here's the biggest crux of the foundation right here. So the rest of it, awesome. So once we finish up chapter 2, we jump into derivatives, and we're like, oh yeah, that's all the stuff we learned in chapter 1. So we're going to kind of pile in a whole bunch of things here. Good. So 2.5, the precise definition of a limit. Here it is. Total fun stuff. I like the intuitive aspect of limit. I like the graphing part of limit. And this one kind of gets a little hair-raising. How about that? We'll go with that. Okay. And so, but we do have to cover it, at least to have to understand it here. So let's go with it. So first things first, the definition here. So let f of x, which is a function, first of all, it has to be defined. Oh, and let me actually spell correctly here. It is defined for all x, as long as it's not equal to a, over an open interval. And this book uses a lot of English words as opposed to a lot of math conventions here. So I have to write stuff out. Containing a. So we have this little open interval. A is in there somewhere. We good? And so now we're going to say this. Let L, capital L, be a real number. A lot of English words, then we'll get to there. Then, here's what we got. Limit as x goes to a of f of x is equal to L. So we have a limit, that's for sure. We have that if for every epsilon greater than 0, so epsilon's kind of like a squiggly capital E, but it's actually a lowercase e. That is a delta. That is a delta. Delta greater than 0. So for every epsilon greater than 0, there exists a delta greater than 0, such that delta is positive, and then we scrunch x minus a absolute value in between there. Writing out stuff, and then we'll sort of piece it together here. So we have a limit. If for every single epsilon that's given to me, I can produce a delta that's greater than 0, so that I can scrunch delta to be the highest value, right? And notice it's x minus a, so that's the x variables, right? That's the y-axis. So sorry, that's the x-axis. Okay. And then notice when we come to the next one, f of x minus 4. Sorry, I don't know. Minus L. Sorry, L. Those are the pins. I'm so sorry. F of x minus L is less than delta. So we got these little scrunchy things that are happening here. So
the x-axis minus where you're going with on the x-axis and the y-axis minus the variance or the
absolutely. Let's draw a picture. Let's see if it helps with a little picture here. Because once we see it, that makes so much more sense. A picture with 1,000 words. Here we go. So we have, I'm going to go like this here, big graph here. And let's see which way. Do I want to graph it here? I guess I can do that. Yeah. I'm going to go like this because it's a lot easier to pinpoint. And so I have a limit. It's called L. We've been doing this all this time. And this is A. So that's true. Right there. We're good. A does not have to exist. We're good. But anything around it has to exist, right? Because that's what a limit is, right? And so then we have this. We have an open interval. Go like this, like this. I have an open interval. And that open interval is caused by, we have limit minus epsilon. And then we have limit plus epsilon. Good there. So I have this little open interval. Too far here. Sorry, class, 1 second here. That should not be f of a, that should just be a.
Because F of A would, F of A would be what the limit would be L, right?
Okay, so it means as I get, and I'm going to put this little x inside here. So x is here, and there's your f of x. So we have a f of x is defined, right? So let's go back to reading our definition. Now we'll get to the stuff here. So f of x is defined, yes. F of x is defined for all the stuff except for a, because we don't need a to be there. Over that. So it's open interval. There's an open interval in parentheses here. Let L be the limit. We got that one. There's the L, the limit. And if we have the limit as x goes to a of f of x as x approaches a from this side, we can also go from the other side as well, right? And here's our definitions here. So for every epsilon, I get an epsilon. I set up an epsilon. I can find a delta that will match that, what I need to do. So that, and then this little play right here, so that absolute value, so this is my little delta here. So write this in real quickly here as we put it in. So I got this little interval. This right here would be L A minus delta, and it goes up to A. We're good. That's my little interval right here. And then my next interval is A, and it's A plus delta. We're good. So my delta goes in this direction, and my delta goes in that direction.
Is the A just?
A is the exact same point that gives me the L value. All right, so next thing is, remember how we've been looking at this in terms of graphs, right? Graphs, we technically say that's great, but they're not precise, right? So then we're going to try to set this up algebraically. So this works on this part, this works on this part here. So, all right, there's the definition, there's the graph of it here. Let's jam.
What are the top two?
Right here.
Yellow.
L plus epsilon. And then this is f of x. So this is L plus epsilon. Okay. Let's go with it here. Exercise 1. We're going to prove it. Here it is. Prove that the limit as x goes to 2, and we'll start off very simple at first here. How about this? And just check it real quick here. Is that true? Absolutely, that's true, right? This is an easy one. You can plug in the 2 into the x. 3 times 3 is 6. 6 minus 5 is a 1. Done. We know that to be true. Okay, so now let's prove it. start off with the easy proofs, and we'll move on to playing with it here. So let's see the setup here. So it says this. It says the function itself, fx, right, minus L, is less than epsilon. Are we good there? If I can satisfy this equation right here, so this is x minus 2 is less than delta. Okay, good there. That's based upon the definition itself. So now let's work our way through it here. And so the easy ones, these are the linear ones, these are the easy ones. We're just going to make sure that the right side and left side are exactly the same. If we can get to that point, we got it. Good. So let's see how this works here. So if I were to get rid of the parenthesis here, I go with that. I go with a little bit more work, and I got this on my hands. Everything good so far. And I can pull out a 3 out of this. 3 is a positive number, and I get this out of it, and I am good to go. Are we good? And then we can divide by 3. Are we okay dividing by 3? So here's what I got here. I can bring this all the way down without changing anything. I'm going to bring this all the way down, and it's still if. And notice that my absolute value is exactly the same. So here's what I'm going to do. I'm going to say, look, I can find the delta. You give me an epsilon. Anytime you get an epsilon, I'm going to divide it by 3. And I'm going to choose either that value or anything lower. In fact, I'm going to choose anything lower than that value. So here's what I get. Any delta that's less than epsilon over 3 is going to fulfill the requirement for this to work. Looks a little abstract here. Let's go back to it. Not equal to, but I want the delta even smaller than that. So as long as the delta is smaller than that, I get what I need. So let's go back to our chart. Fun stuff. There it is. It's any epsilon you give me, as long as I divide by 3 and give me something smaller for the epsilon than for the delta, I'm good. There's my limit. I can always get smaller than what you give me.
Is that just
But no, yeah, that's where the math comes in. Is what kind of math are we going to get in order to get to where we need to get to. So sometimes delta is equal to epsilon. Sometimes it's the minimum between 2 values. Cool. So let's go back, look at a picture. Let's see if this makes sense. 3x minus 5, everybody okay with this right here? This is the way it normally looks. 3x minus 5. We're looking at as x goes to 2, maybe like somewhere here. And then the value is 1. And let's see if this makes sense to us here. So if I say my epsilon value is going to be 1. So remember the relationship right here, right? Let's say epsilon is equal to 1. Let's just do it that way. And so notice my value is epsilon can go down to 0, or my epsilon can go up to 2. Right? If that's the case, what's this value here? If I get 0, what's this value here? What's the open interval that I need to look at? What's x going to give me? I don't know. I think if I plug a 0 and 2, that's a 1 there, right? If I plug a 0 in for here, add 5 divided by 3, everybody okay with 3/5? So that would be 3/5 is a low ball figure here. 2, if I plug in a 2, both sides, divide by 3, we're good there. And so this is 7/3. Okay, so here's my little interval. And it says, hey, you give me an epsilon of 1. And I say, look, as long as I'm inside this little interval between -5/3 and 7/3, I would be okay. In fact, you give me an epsilon of 1. Well, let's take it in 5/3. 5/3, sorry, should be positive 5/3, positive 7/3. That's my interval that I'm sort of reaching. The question is, can I find a delta in that interval that will get me closer to L than you got me closer, that gets me closer to A than you got me closer to L. So if you gave me a 1, I have to get some, delta has to be something that's less than 1/3. Good there. So how about if I say 1/5? Is 1/5 smaller than 1/3? Yeah. So notice if I was going from 2 plus 1/3 would give me 7/3, right? It gets me to this right here, right? And then 2 minus 1/3 gets me to 5/3, right here. Good. So if I say 1/4, I'm going to be in this little area here. So I found an open interval that's smaller than the open interval you wanted me to find, but I can still have L as my limit. Okay? That's the precise definition of limit right there. It's I can give the smaller interval that you made me do. All right, that's the math behind it. What we say is we at least got this to be looking the same. And once that looks the same, you gave me this, and now I have a proportion that I'm going to use. And as long as my proportion is smaller than your proportion, I get my little window or get my little interval. Are we good? Yeah. See, that's the fun part. It's, oh no, yeah, this will be a fun ride. Okay, so the fun part is this. Some people say, like, yep, that totally clicks. And some people are like, nope, that does not click. So let's do, that's the explanation. The rest we're going to just kind of grind the algebra out of it. Okay? So the explanation, yeah. And so let's talk about it. Let's do that. Let's talk about it. Let's see if that's kind of just kind of mull it over a little bit in our minds here before we go on.
Grinding the limit as such, just because that's what we say. We just say, I'm going to call this a limit. And it's not like you're proving that the limit is. That's what you're saying. This is what a limit is. And I'm going to show it.
Yeah. So I'm saying this is the limit, and we know this is a limit because by our little limit techniques, I can find a limit here. I can plug in the 2 into here. That makes 6 minus 5 is 1. I can do my techniques of finding limits there. This is the proof that it actually is true. It is part of the calculus sequence, and there are math teachers, professors that have crunched for time, they'll leave this out. Yeah, but it's just a matter of like when we got to the foundation, this is the foundation. This is the theoretical foundation behind limits.
And you're showing, so it's
When I went through calculus the first time, yeah, the lady did skip it. Then I went to like, what is this? And I had to relearn it. Go ahead.
if you have like that problem and you want to find this, if saying this is the same thing as finding the limit, it's just a way to show that it's true for evidence and actually figure out something that looks like it's true.
Yeah, very true. All right, let's do another one very similar to this, just to get our understanding of it here. So can you guys do this here? Prove for me limit as x goes to 1 of 2x, it's plus 1. Okay. All right, very similar as the first one. Let's So first of all, let's make sure that it is. Is that true? Yeah, it's a linear function. I have no domain problems here, right? So I don't have to factor, I don't have to cancel, nothing like that. I can just plug in the 1 times 2 is 2, plus 1 more is 3. Yes, that is the limit. So now let's prove it.
Did we memorize like the whole, like the f x minus the limit, and then is rid of the variable epsilon? Did we memorize that?
Yeah, because based upon the definition, here's what we got based upon the definition is the function itself, 2x plus 1 minus the limit itself is less than epsilon if I can find a delta that as x goes to 1, I'm going to have that charge there. All right. So linear ones, these work out very nice. So drop the parentheses, combine everything together, take out the 2, and once you do that, everything's nice. So I have the same exact connection there. I can bring this all the way down. And then I need to get delta still to be less than that. Good. So that my pick is any delta that's still less than epsilon divided by 2. Okay, are we good there? Yeah. The feel of it is that, once we saw the little graph, right? We can take a look at the graph again, but it's really just, you give me 2x plus 1 would look like this right here. And limit as, it's going to be like right here, 3. That's going to be 1 at this point. And so the question is, if you give me an epsilon limit, I can get you a delta that's tighter than that. And a delta is going to be less than 1/2 of that. And so you give me an epsilon of 1, I give you an epsilon of less than 1/2. You give an epsilon of 1/2, I give you something that's less than 1/4. And I got myself an interval that still has that. Okay, good there. Does that make a little more sense? Maybe. Also, I have to give you guys a study guide on this. I should give you guys a study guide tonight sometime. Okay, that's the linear forms. We're good? Now let's start something else. How about the quadratic forms? Just piling it on. Eli says, come on, bring it on. Okay, so now what happens with x squared? That's the issue here. So here's the process. Prove this beyond a shadow of a doubt, beyond any mathematical shadow of a doubt, that this is true. All right, this one gets a little bit more complicated. All right, let's go with it here. So setup is, let's let's see, x squared minus 4, right, less than epsilon. If 0 less than delta x minus 2 is less than delta. Are we good there? I think we're good there. Okay, let's do a graphic here. Let's kind of see what we get to here. X squared looks like this. And we'll place 2 right over here. And that's for non-drawn scale. Okay, we're going to do a little piece here we want to do. So first things first is we're going to say that epsilon, we're going to choose an epsilon that's going to be less than or equal to 4. Go there. First things first, let's do that. That'll help us out in just a bit here. So if I choose something epsilon less than or equal to 4, you know that makes my delta to be a positive value. Everybody agree there? The delta, because if I go down to here, that's going to be 0. If I go up, that's going to be 8. So I kind of spread it between 0 and 8 as like the widest this could be. Good. Okay, if that's the case, that means if this is 0, I got myself this space here, and this space here is the widest thing I need to look at. Okay, how does that help me? It helps me reduce this little piece right here. Very good there, which is not really, just notation wise, right? For sure that's true. Okay. Processing, good. You guys look nervous, so I just want to make sure that we're okay still. Next is this little piece right here. So this little interval that I'm looking at. If I say epsilon, epsilon's going to be somewhere in this range, right? So down here, if we look at it, this would be 4 minus epsilon. Are we good there? And over here would be 4 plus epsilon. Are we good there? So this little, now I got my little closer range. That's my closer range. And that's my little closer range right here. But notice that epsilon going this way on the left side, right, is much wider than epsilon going that way, right? Because it's going up faster, right? So that's why you can't just say like, oh, I'm going to take the right-hand side or the left-hand side. It's whichever is the interval that's the smallest between the two. That's what we're looking at. Okay, so now I'm thinking about, okay, let me think about this range right here and this range right here. This is what I want to see. And that range of things, you guys agree, this little piece right here is going to be 2 minus the square root of 4 minus epsilon. We'll get there in just a second here. See how we got that. It's a square function, right? So if that's the square function, to get us back to where we were before, it would be a square root function. Okay, this side right here, still moving around. No way, I think I just erased. No, we're on 3, right? Okay, let's go this way. This way is going to be a little bit different. This one's going to be, the top function is the square root of 4 plus epsilon. Is that right? Topmost on the side, 4 plus epsilon. That's going to be minus 2. Bigger minus smaller in that case. So linear functions easy because they're all going to come out to be the same on the delta and epsilon. With the square functions, they're not going to be the same now. Now they're going to be in terms of what interval do I want out of this. Okay, so now I think we can begin. let's start this. Let's see if this makes sense. So now, because I've defined epsilon to be less than or equal to 4, I got this little thing on my hands here. So we'll start from here. This will be, so this piece right here, tell me if you guys agree from algebra. Are we good there? I can get rid of the absolute symbols, but putting a little negative on the other side. Cool. So in that case, all I want to do is I want to see if my function itself can be couched in that set of intervals. So let's see if this makes sense. I'm going to place now the ints right here. So I'm going to put in a new int here called 2 minus the square root of 4 minus epsilon. That's going to be the negative of it, because I want to move the negative side here. And it could be equal to delta. That's fine. And this is going to be, okay, so that's, tell me if you guys, it's this little interval right here. It's this little interval, that's the lower interval coming in on the left side with a negative behind it. It's the top interval coming on the top. So if I can, now if I can do this, I want to squash this in epsilon so that I get back to my function itself. If I can do that, I made my little interval. Okay, so let's do a little bit of algebra here. Distribute the little negative here. We can drop the delta out of here because we're looking for the epsilon at this point here. We know delta is scrunched up inside there. And so negative 2 plus x minus epsilon, x minus 2, and this will be epsilon minus 2 over there. All right, what are we trying to get in the middle? We're trying to get x squared minus 4 right here. We're trying to develop this little piece right here. So can I add, let's see, add 2's everywhere. And I'm left with that right there. Are we good there? Let's see, I can square both sides. Are we okay with me squaring both sides? Think about it here. If you have 3 that's less than 4, less than 5, if I square them, interval still stays? Yep, so I'm going to square, square, and I'm left with 4 minus epsilon less than x squared. That's less than 4 plus epsilon. And can I subtract 4 from everywhere? Yep, sorry, I'm running out of space here. I'm going to subtract 4 from everywhere. That gets me to something like this. And I can now, this is the definition of absolute value. So x squared minus 4 is less than epsilon limit. Okay, so then let's see what how do we do the logic here? So we said, look, if you give me an epsilon, I give you a delta. And I said, okay, that's fine. As long as we say, look, we're going to look at very small values of epsilon. Anything less than 4, that's cool. If it's greater than 4, then it's too big. I can pick it for you. Give me 1,000. Epsilon's 1,000. Who cares, right? Because it's too wide. It's the narrow ones that I'm looking at. So as long as epsilon is less than or equal to 4, I can make an interval here that will fit underneath the condition that you gave. And then as you do that, you get back to the condition here. So it's more like it's more like this. Logic is Eli gives me a number, a small number. Eli says 0.1, right? And I say, okay, that's fine. Look at this. If I use 0.0005, watch this. And as I do the calculation, I get smaller than his 0.1. I get look, I got a 0.9. That's kind of the logic there. Okay, so he gives me, let's say he gives me 1. And I say, okay, I'm going to use 1/4 in my equation. And as I do my 1/4 equation, it turns out to be only a half, right? So I say, look, you gave me the 1, I gave you back the 1/2. Okay, crazy, overwhelming, weird, or pretty cool? Which one? Tedious is the other thing that could come out. No reaction. Okay. We got another one here. Let's see.
We're trying to get the limit, okay, the range minus the one that is left of one if the other thing. Why do you have to why is the
Over here?
I can't see right
Sure there.
Oh.
Is that what you're asking for? The equal sign?
No, no, like at the very beginning, just like on in each of the problems, not specifically with this one. Well, I guess it wasn't so bad. Like this, why do we want to put these two sides equal?
Because you're saying this. You're saying that if I give you an epsilon value, you can find a delta value that will make this true. Sure, sure. It totally will tell you here. So here's so you're saying here's my epsilon I'm going to use, right? I said, okay, let's at least make it less than 4 or equal to 4, right? Based upon that, and a little diagram here. So if you subtract epsilon from L, the interval that we formed, the highest interval that we formed is this little piece right here. So as you do this, I'm saying, let's say you give me the epsilon, right? Epsilon says, here's your epsilon. Okay. I go back to my formula itself and say, okay, this is the interval that I'm going to have to be in order for this to be true. And as long as I'm here, I fulfill this little criteria of it being my epsilon could be equal to, my delta could be equal to that, or the same as that. Or on this side would be better. Equal to that or less than that. And so as I form, I'm forming this little interval. That's me. Like, I'm going to form this little interval. I say, okay, I got it. I'm going to form my little interval. And as I do it, I come back to this and say, look, I fulfilled your requirement. So it's almost like I'm coming back to you and saying, I've done what you asked me to do. I found the interval that will be inside what you asked.
So it's like you're trying to define the limit between like the limit and will be turned smaller and get
Absolutely. Absolutely. That's exactly what it is. Yeah. I'm trying to find an interval that will fit inside. For linear functions, it's pretty easy because you have this little piece right here. You're saying, look, I got that little piece that would work as long as this condition is met.
So how do I always know that that's going to be that true that if the epsilon minus level is less than epsilon then how do you know that that is always going to work?
Because that is the definition of a precise definition.
So it's just like who cares or that's what you're saying a little bit. So it doesn't matter if it's something else. That's what we're looking at everything.
Yeah. Based on just the definition. Okay. You guys talk to me. No, it's a precise definition because
no, but the limit is not something
we're just saying it exists. That's all. That's what we need to get. Okay, guys, I promise that starting chapter 3, like the sun's gonna come out, and like all of that totally makes sense. We're good. Just that. How about this? I'm gonna give you. I'm gonna give you a linear one on the test. As long as you guys do that one. So the first 2 examples. That'd be good. I just want you at least to read to it. Okay. So that'd be easier. Ooh, that's right. We talked about that here. Let's see. I do want to make it standardized, so I almost want to go back to those just those basic limit formulas. That would be it. And any formulas that I can come up from chapter 5, I guess the definition of exponential function, definition of logarithmic function. Anything that's blue, how about that? That has formulas inside it. That kind of like stuff like this. I have the PDF version of the textbook, so I can just cut and paste, and I'll make it. How about that? I'll send it out to you guys. This is what you guys can have. But it's literally just gonna have those little formulas. Yeah. This thing gonna be on. The definition of limit, or the definition. Yeah, I should give you the definition of it. Yeah, that should be at least. Or I'll write it the way the book writes it. And the jump continuities and the other continuities, right? It is very wordy. Okay, got 15 more minutes here. Let me do one more. Let's see, should we do? I think we can do it here. Can we change it up? Let me change it up to 4. And it is different for each one, yeah. So that's a little problem. Okay, this one. So based upon what we just did on the previous problem here, can we try this one together? And then I have one more that we can try. That's not good. I think we do that. And these are perfect squares. Because they're perfect squares, this lends itself a lot easier. If you don't have perfect squares, then you got a little bit more precision. Again, this is technical. This is very gut precise stuff. Okay.
So we just say that we just define epsilon.
Define epsilon. You can say it in a sense of it is arbitrary, but then you're picking something so wide that would just totally make sense. Like epsilon being less than or equal to 9 in this case. That's a big wide margin.
So like we picked 4 in the last one. We could have picked 5 or something.
We didn't want to go into the negatives because we wanted delta 10. So that's the only condition.
Okay, but we could, for this, we could pick 8. Like, it doesn't need to be, if there's not specific to one of something other than just one of the
Yeah. So there's my little condition. So I'm going to say that epsilon has to be less than or equal to 9. That's my first condition. If that's the case, I get 9 here. That means I'm not going to go to the negatives. I'm going to go to up to 18. This is 9 plus epsilon. Somewhere in here is going to be a 9 minus epsilon somewhere here. But my condition is the bottom goes. I'll look at anything from 0 to 18. All right, x squared goes like that. There's my little 9 that comes down. There's technically my 3. All right, and let's go with it here. So that means this is going to be this little interval right here. Figure out what the interval will be. This is going to be the square root of 9 minus epsilon. This little piece right here. The piece on this side is going to be the square root of 9 plus epsilon. And my range here is going to be 3 minus 9 minus epsilon. My range here would be epsilon 9 plus epsilon minus 3. There it is. It's how far I'm extending my delta. And let's see, I'm going to see if you can look back at the previous problem, see how far you guys can go. By defining epsilon less than or equal to 9, takes out this little 0 here. That means it allows me to have a negative delta on this side. Positive delta on this side. And I'm saying my delta is going to be smaller than this, or equal to that, because I already defined my epsilon. So again, it's almost easier to see it on the right hand side here, right? So my function, there's my delta. My delta, the farthest I want to get out is to go like this. Now the question is, can I get back into my original function? Notice on the linear forms on both sides, they gave you the same exact value, right? Because the math has to work out. Yeah. Yeah, we can take out the deltas out of here because in terms of epsilon only. So -3 plus. Because we want everything in terms of epsilon. Right? We're trying to get back to this. So by us defining this little interval, I'm saying, yep, delta is going to be inside there. The way I defined it. Now I'm going to try to get back to my original problem, see if I can. So adding 3 everywhere. Squaring. Oh, that's not. Take the square root of each of those. Adding 9 to each of those. And eventually I get back to my condition as long as my interval is there. Now, you chose a smaller interval. Absolutely, right? But that's the way we defined it. Based on delta. Okay, one more. Let's see. This one can be a little bit more of a touchy one. Like I said, and after this, it's going to be purely awesome all the way through the rest of the book. Okay, so do these guys get tough? Absolutely. We have not even looked at rational functions yet. have them look at the square root functions. We haven't even taken a look at those yet, right? Because those are again a different animal. You have to figure out how is it precisely going to work here. Okay, and if you get stuck on, let's do this with disclaimer. If you're stuck on the homework, you can throw your book across the board. Just like chill and let's come together on Wednesday and okay. Yes, no. Yeah, it starts off like it's gonna be tough because there's x squared minus 9 over x minus 3. But hold on, though, hold on. What do you? You could just separate them. Yeah. And it just has a hole there. Yeah. Let's see if there's any others. Yeah, and one of them is just rewriting the definition itself. One of them is a linear function. One of them is the ones that we covered here. And one of them I'm going to have you struggle with covering. Okay, let's do this one just for you guys to see it here. Example 5. So I'm going to do this here. Limit. Let's see if we have time. I think we'll have time right at the end. Limit as x goes to -1 of x squared minus 2x plus 3 is equal to 6. Okay, guys, check me on that one. Is that true? First of all, is that true? I do want to just sort of let you see something right here as we do it. And we're going to go kind of fast here. Just going to see if you can think through it as I write it down. Okay, and check with me. Is that 6 is good? If I plug in a -1 into that. -1. That's a 1 plus 2 plus 3, right? 6. Cool. Okay. I think I'm going to a -1. So let's go with it here. So let's write the epsilon condition. X squared minus 2x plus 3 is less than 6. It's going to be less than epsilon. Look at there. If this would be x plus 1 this time, there would be x plus 1 this time. Cool. Okay. All right. What do we do here? What do we do? Well, we have to play a little game here. And on the last one, when it was just x squared minus 9, right? That was easy. It's nice. This one, you have more things to do. So this is kind of like the linear function. Let's simplify this. Let's simplify this a little bit here. I'm going to go kind of fast here just so we can finish up here. And so we do this here. You guys talk to me. Is this okay here? Okay, even more so. Can I keep on going? So I'm going to, is this true? Plus 1, is that right? This right here. I wrote epsilon backwards. Okay, we're good there. Oh, wow. Okay, so remember, the x squared minus 9, that did not simplify. It was nice to have it that way. This one, tell me if this is true. Tell me if you guys agree with this. Multiplied by. Is that still okay? All right, true. That x minus 3 is the problem. Because x plus 1, if it was a linear function, we got our linear function. X plus 1 on both sides. We're done, right? Oh, here we go. 4 minutes. So let's do this here. Again, we have to pick. We're going to pick very small values of delta 8, right? It's not like we're going to have 15, right? We want to go small, right? So you know that delta is going to be, let's maybe like write it in here. Delta is going to be less than 1 for us, right? Because that's easy enough. Delta is less than or equal to 1. this makes sense. Tell me if this makes sense. And it's x plus 1. It's going to be less than delta, which that itself is less than or equal to 1. Good there. So it's
just saying, we're just saying normal.
Yeah, just like we epsilon. Smaller. Okay, if that's true, then we have this is true. Everybody read there. Everybody read. Even that already defined it there. That was good enough to be there. But no, I'm not going to negatives. Okay, so here's my little problem. Notice this is right here. If I go this way, what is that? 0? Is that true? You guys talk to me here. Does this make sense? Oh, that's -2, right? That's 0, right? My little problem is that little -3 there. So let's do this here. I'm going to subtract 3, put it all in here, and see what this says right here. This is -5, x minus 3, and -3. We're good there. So notice what I have here. 2 minutes left. -5 is the lowest it can go, right? -3 is the lowest I can go there. Here. So the widest delta can be. Oh, we have absolute value in our hands, right? So if I were to do, again, this gets a little weird here. So let's see. If I take the absolute value of those, of all 3 of those terms, right? So -5 is the lowest piece on our block, right? It gives us the widest range. -3 gives us a smaller range. Good. So let's see if this makes sense here. So absolute value of x minus 3 would be less than 5. There, that one. Or the other one would be less than 3, right? I'm going to say, I'm going to use the widest possible value, which is this one right here. That's the one I want that. Sure, because I took absolute values of it. So I'm going to pick that one for my value. So let's see if we can still go on. All right, if that's the case, then see if this makes sense. So I'm going to expand this out just a little bit here. I'm going to say that this right here, that expand this out just a bit, x plus 1, x minus 3 is going to be less than x plus 1 times 5, less than epsilon. Pretty good there. We're going to divide both sides by 5 over here. And we have ourselves this answer right there. So you gave me the epsilon and the condition stated. I went over here and I said, look, those are the conditions stated, and I choose very small delta values. The largest value I can choose is 5. I plugged it back in, and I fulfilled the condition with this extra little piece of the widest range for delta. Okay, we're past time, so I'm going to stop now. Is Ms. Bayer out there already? Okay, is this a tough section? Absolutely. Students sometimes just fly over their head. Absolutely. So if you don't get it, that's okay. In fact, let's do this here. I'm going to limit the homework. Limit the homework to 1, 2, 3, 4. Let's just do the first 4 problems of the homework. Cut everything else off. We good? So it'd be 177, 181, 189, and 191. That's it. I'll let you guys struggle with 191. 189 is going to be very similar to what we just did up here. 189 is actually the linear form. It's in disguise. You have to cancel off the numerator and denominator. And then, sure, yeah, absolutely. So just 177, 181, 189, and 191 only. That's it. That's the only, just four problems. Okay, so we take the test and then we start after Thanksgiving. Things are going to be awesome. Okay. I'll send you guys a study guide tonight as well. And then after that, come on Wednesday, we'll go with the homework questions. Homework will be a homework day. Come with any homework questions, any questions on the study guide. And we can study for the test.